Okay, so welcome back from your coffee break. So the next speaker is Monika Kudlinska from the University of Oxford, who will be talking about quasi-isometries of free-by-cyclic groups.
All right, great. So thank you very much. Thank you for organizing this insane conference and for inviting me. So I'm going to be talking about free-by-cyclic groups. No surprises to anyone who knows me in the audience. And in particular, I'll be talking about quasi-isometries of free-by-cyclic groups. So let's just double back a little bit. The whole motivation for studying fibering comes from topology, from manifold theory. People are interested in this notion of manifolds fibering over the circle, which just means that your manifold is the total space of this fiber bundle, where the base space is a circle, and necessarily the fibers are just codimension one submanifolds of the same homotopy type. So it was sort of the content of a very famous open problem for a long time, where the hyperbolic three manifolds fiber over the circle. And sorry, here I should keep saying over the circle, really. And this was proved to be the case by a bunch of people, in particular Przewalski-Wise, and then Agel kind of tied everything together. And they proved that actually, yes, all hyperbolic three manifolds do virtually fiber. So as long as you allow yourself passing to finite index covers, you can obtain this nice fibration structure. And then it was natural to ask, okay, what about higher dimensions? So in fact, if I have an even dimensional manifold, then I can't fiber over the circle just for reasons of Euler characteristic. So then, of course, what about 5 manifolds? That's the next odd number. And again, this was a very recent and important result that came out by Italiano, Martelli, and Miglorini, where they showed that they constructed a bunch of these hyperbolic 5 manifolds, which do admit fiberings onto the circle. Okay, and this wasn't just interesting to manifold theorists and topologists. This was actually also something that interested group theorists, because it actually gave us first examples of hyperbolic groups with subgroups which are non-hyperbolic and a finite type. So this was, again, also an open problem in group theory and geometric group theory for a while. I think it was Brady who came up with first examples of such non-hyperbolic subgroups of hyperbolic groups, which were finally generated. And then people ask, well, what about finite type? And here, when I say finite type, I mean it's the fundamental group of an aspherical CW complex, which is compact. So fibering over the circle is a phenomenon that's interesting and that leads to kind of open, solving questions not just in manifold theory, but also in group theory. That's sort of my point here. But we can generalize this and just abstract it onto the notion of fibering of a group. So we say a group algebraically fibers. I'm going to drop the algebraically pretty soon. If there exists an epimorphism of that group onto the infinite cyclic group with finally generated kernel. So that's crucial here. And free-by-cyclic groups are examples of such groups where the kernel of this map to Z is a free group. So here I'm using maybe slightly non-standard notation, non-standard terminology, because sometimes when people say free-by-cyclic, they allow this free fiber to be infinite rank. But here, I because of my definition of algebraic fibering, I'll always have this this free group, this free normal subgroup being finite rank. And well, some people say this is finally generated free bicyclic. Okay, so I sort of introduced free bicyclic groups in a slightly opaque way for a reason that will become clear later on. But if you haven't seen these before, they're groups that admit these very nice presentations. They're just semi-direct products of free groups by an infinite cyclic group. So you can construct such a group just by taking some free group of rank n greater or equal to 1, and an automorphism of this free group. And then you just take the mapping torus of this guy, algebraic mapping torus. So it's just, again, semi-direct product or an H and N extension where the base group is this free group. This probably won't be necessary later on, but this automorphism phi is called the monodromy of this fibrine. And again, an interesting fact that won't really come into play in this presentation in particular, but something that's a big part of my research is that when you have a free-by-cyclic group whose free abelianization has rank at least 2, then your free-by-cyclic group fibers in infinitely many different ways. So you can find, in particular, you can find, these free-by-cyclic decompositions where the free group has arbitrarily large rank. And so you have this whole family of automorphisms, and you can study what do these guys have to have in common, what algebraic properties, or how the algebraic properties of the free-by-cyclic group restrict these dynamical properties of the automorphism. So that's something that's interesting to me, but won't be relevant today, but I just wanted to mention anyway. Okay, so free-by-cyclic groups, even though they admit these nice presentations, they're actually a class of groups that exhibits also a very wide range of behavior. So there are not that many things that you can say about all free-by-cyclic groups. There are many results that restrict a certain class of free-by-cyclic groups. But there are a couple of things we can say. First of all, they all have cohomological dimension 2. So that's something that's going to be relevant later on. I'll come back to that. Don't worry if you don't know what this means yet. They are all coherent. So every finely generated subgroup is finely presented. This was proved by Fein-Handel. And actually in this paper, it's interesting, they come up with a whole characterization of subgroups of free-by-cyclic groups. So we sort of know what their subgroups look like, which is pretty amazing. Another property is residual finiteness that's satisfied by all free-by-cyclic groups. So every non-trivial element, for every non-trivial element, there exists a finite quotient of the group where this element doesn't die. Okay, so these are all, you'll notice these are all algebraic properties. And somehow it's easier to prove things like algebraic things about free-by-cyclic groups than stuff about their geometry. So we do have a result of this type, which says that all free-by-cyclic groups have quadratic Dane functions. But this was, whereas the previous results didn't really require so much work, they were fairly short papers. Quadratic Dane function was a huge undertaking, and there's a whole monograph proving this thing. So it's quite hard to prove things about the geometry of free-by-cyclic groups. And actually, so as I said, they exhibit a large range of sort of these negative curvature properties, but we can't say that they are all cylindrically hyperbolic unless they're virtually direct products. But that is sort of all we can say about all of them. Okay, some of them are hyperbolic, some of them are not hyperbolic, some of them are not even relatively hyperbolic. Okay, so these are the properties that we know for all of them. And then there are things that are still open that are, so for example, we don't know whether all the automorphism groups of free-by-cyclic groups are finally generated. This is still open. It was proved in a special case of linearly growing monodromy, and where the fiber has, where the fiber has rank at most 3 by Andrew Martino.
Excuse me.
2 years ago. Yeah.
Hello.
Yeah.
So, I mean, free-by-cyclic group, they are acylindrically hyperbolic?
They are cylindrically hyperbolic unless the monodromy has a finite order in the outer automorphism group of the free group. So yeah, so unless they're virtually direct product.
Yeah. Okay. I mean, most of the group you are saying acylindrically hyperbolic, or?
Yes. Yes.
Okay, I see. Okay, fine. I mean, any reference for this?
Reference for this, I don't remember off the top of my head, but I know how to find it very quickly, and I can put it in the chat straight after.
Okay.
Yeah.
Okay.
All right. Okay. And any other questions about this? Right. Great. So we don't know about their outer automorphism groups. There's very little known about that. And we also don't really know anything about their behavior under quasi-isometries. So this is something that's and this is the main topic of this of my talk. Okay, so just a quick recap on quasi-isometries. I feel like this audience is probably fairly comfortable with this, so I will go fairly quickly. Given two groups with word metrics, a map between those groups, and here I really mean a map, it doesn't have to be homomorphism. It's a quasi-isometric embedding if it's coarsely by Lipschitz. Okay, and here you can quantify what this means. So you can control the distance between the images of 2 points in the codomain with the by the distance in the by their distance in the domain. And furthermore, this map is said to be a quasi-isometry if it's coarsely dense. So for every element in the group H, there exists some G, which is uniformly close to, mapped uniformly close to it. Okay, and the motivating question of, well, geometric group theory, this is something that, well, the study of quasi-isometries was really instigated by the work of Gromov, and he was sort of posed this question, well, how much of the algebra of the group is preserved under this quasi-isometry, under this geometric map? Okay, so just to make this question a bit more precise, I need to define a couple more things. So we say two finely generic groups are virtually isomorphic if I can find some finite index subgroups and then some finite normal subgroups of those subgroups where the quotients are isomorphic. So essentially these groups are the same up to some finite error. Virtual isomorphism implies the groups are quasi-isometric. And the big $1,000,000 question is, when can this implication be reversed? Okay, so this leads to this whole study of the notion called QI rigidity. Right, so a group is said to be QI rigid exactly when this implication can be reversed. So whenever there's some group that's quasi-isometric to it, that group has to be virtually isomorphic to G. Okay, so all the groups in the same QI class as G are groups are virtually isomorphic to G. And it sort of makes sense to generalize this definition a little bit and just talk about a class of groups being QI rigid, which is exactly what you think it would be. If I have a group that's QI to some group in this class, then it's virtually isomorphic to perhaps a different group in this class. Okay, and there has been a huge amount of work done on QI rigidity since Gromov started this. And I'm not going to name all the, well, even state all the results, but I'm just going to say a couple of really basic things that you would hope are true. And the first one is, so finite rank free groups are QI rigid as a class. The class is QI rigid, but actually individually they're not. So they're all quasi-isometric to each other if the rank is at least 2. And now something a bit closer to home. So closed hyperbolic 3 manifolds, this class is QI rigid as well. But in fact, this is just Schwarz-Milner. So they all act geometrically on the hyperbolic 3 space with a hyperbolic metric. And so they're all quasi-isometric to it, and so quasi-isometric to each other. And here, of course, open problem is the class of free-by-cyclic groups QI rigid. Okay, so, and I repeat, like, we know very little about quasi-isometries of free-by-cyclic groups in general. So this is very wide open still. Okay, so why should we believe this to be true or not true? Where the reason why I stated the free-by-cyclic group definition the way I did was because I wanted to draw attention to the fact that free-by-cyclic groups are groups which satisfy a certain property, and that is they admit this map to Z, this epimorphism onto Z, with finely generated kernel that is free. And so this is the property that we would really like to be preserved by quasi-isometries. So the first piece of bad news is that actually the property of admitting a homomorphism onto Z is not a QI invariant. And you can see this by looking at the Berger-Moses groups. So these are simple groups, but they're lattices in products of trees. So they are QI to direct products of free groups, which do admit maps to Z. but of course they're simple. The kernel is a normal subgroup. So admitting a homomorphism to Z in general is not a QI invariant. However, good news, and this might seem a bit out of the blue, cohomology dimension of groups is a QI invariant if it's finite on both sides. And we'll see why this is something that's actually very good. And in general, group cohomology behaves nicely with respect to quasi-isometries. So this is a fact that we're going to exploit, and this is what sort of what makes the theorem work. Okay, so theorem. I'm going to explain all the terms in a minute. So suppose I have a group, and this group has finite cohomological dimension. And suppose also that G has this property that we've already actually seen before, mentioned in Hone's talk, that it's refers. So that stands for residually finite, rationally solvable. Actually, it's virtually refers. So it doesn't have to be refers on the nose. If this group is quasi-isometric to a free-by-cyclic group, then this group is virtually a free-by-cyclic group. So in other words, the class of free-by-cyclic groups are QI rigid amongst the class of refers groups of finite cohomological dimension. Okay, so we'll come back to the cohomological dimension business in a second. Refers is something that, again, I actually don't want to talk about in too much detail because it's just a fairly long definition that's not very illuminating. But roughly what it means is that every finite subset of my group can be separated in the urbanization of some finite index subgroup. This notion stems from the work of Ian Agel on the virtual fibering conjecture. Yeah, so examples of refers groups or virtually refers groups include subgroups of rags and all virtually special groups. Okay, so where does this come from? How does this work? So we need to do just a quick detour into the world of group cohomology. It's something that's a very useful tool to study infinite groups. It's a sort of representation theory type tool result. And so I think it's just worth knowing. I'm not gonna really talk about things in too much detail, but I'm just gonna mention roughly what's going on. So we have a group G, and we fix some ZG module M, which is just an abelian group with a nice G action by automorphisms. The cohomology groups of this group with coefficients in M are just a bunch of abelian groups, right? That are indexed by the positive and non-negative integers, and the same for homology groups. So the key example is a sort of, you already use some homology and cohomology groups in everyday life. So if you're looking at the abelianization of your group, that is just the first homology group of G with coefficients Z, where Z is just the group, the ZG module with the trivial G action. So it's just the integers and the group acts trivially on it. So H lower one of G with coefficients in Z is just your abelianization. And H upper one of G with coefficients in Z is the group of homomorphisms of G to Z. Okay, so it's just a dual. Okay, but somehow if we just restricted ourselves to studying cohomology and homology with the coefficients in the trivial Z module, then okay, you couldn't, well, you'd be missing out on a lot basically. So in fact, varying the coefficient module really can shed light on properties of your given group. So for example, if you look at the cohomology of G with respect to with coefficients in the ZG, so just the group ring, then this detects splitting over finite groups. So it detects whether your group is infinitely ended. And we'll come back to how this is used. This is basically the main result in proving the Stalling-Swan theorem. Okay, and even more interestingly, so if you look at the coefficients that are given by L2G, so these are the square summable functions from G to the complex numbers, then even more interesting things happen. And things that I did, first of all, I'm kind of sweeping a lot of things under the rug. So here now, it's actually okay because I didn't really define what group cohomology even is, so I haven't lied to you. But when you look at this L2 cohomology, it's called, you kind of have to, it's more of an analytic notion. So you have to, instead of taking the cycles questioned out by the boundaries, you have to question out about the closures of things. And when you take the Betti numbers, you're actually looking at not just dimension, but this thing called the von Neumann dimension of the homology groups. Okay, but we're going to come back to this. So I'm going to be talking about these L2 Betti numbers, which are these somehow these dimensions of these homology groups, but in a way that's not as straightforward as you might think. Okay, so cohomology dimension and finiteness properties. So this is sort of a key thing. So a group is said to have cohomology dimension n over the integers if for every dimension d greater than n and any g modulo m, this cohomology vanishes. And in particular, if a group has cohomology dimension 1, then actually it's free, and the converse holds as well fairly trivially. So it being of cohomological dimension 1 gives a characterization for a group being free. And this is a very important result. So you see, so our free-by-cyclic groups, they have cohomological dimension 2. So it's not quite as good. This doesn't characterize the property of being free-by-cyclic, but it's still quite nice because, for instance, the cohomological dimension of a subgroup is bounded above by the cohomological dimension of the alpha group. So, if we can prove that the cohomological dimension drops by 1 for a subgroup of a free-by-cyclic group, then we know that subgroup has to be free. Okay, and then the other notion that I want to introduce is of type FPN, being of type FPN, which now again, this is where I'm being a bit bad. So I'm just introducing a lot of words that I'm not going to define, but essentially it means that it means that there exists a projective resolution of length n of the trivial Z module via finitely generated ZD modules. Okay, so this is something I just wanted to include for completeness, but I'm not going to define all these terms. But you could, for the lower finiteness properties, it's fairly straightforward. So you're of type FP1 if and only if you're finally generated, and if you're finally presented, then you're of type FP2. Actually, the converse doesn't hold, and so you can think of these as being these higher finiteness properties, being of type FPN. Okay, and so the reason why I introduce all of this is that because I want to be able to prove that group fibers, right? All I know is there's a group that's quasi-isometric to a free-by-cyclic group, and I don't even know whether this group admits a map onto Z. In general, it's not a QI invariant. And so I need to somehow be able to prove that such a thing exists. And I do know that these cohomological properties are preserved under the quasi-isometry. So I need some sort of cohomological properties that will ensure that my group does fiber. And this is exactly given to me by the theorem of Sam Fisher. So this is a generalization of the theorem of David Kilak that was also mentioned in the previous talk. But here we have a group that's of type FPK over Q. If this group is reverse and if the first K of its L2 Betti numbers vanish, then G admits a map onto Z with kernel of type FPK over Q. So in particular, if the first Betti number vanishes, then it emits a map onto Z with finely generated kernel. But for reasons that I'm not going to talk about, I actually need this slightly stronger result of Sam rather than the original result of David. Okay, and actually, so conversely, we don't need reverse or anything, just any group that admits a map onto Z with finely generated kernel, then all of its L2 Betti numbers vanish. So that's something that we know. And then the sort of the final piece of the puzzle, modulo some basic results from cohomology theory, is that the vanishing of L2 Betti numbers is a QI invariant. This is a result of Sauer. So you can put all of these things together, and this is how you can get the theorem that I stated above. Thank you very much.
Okay, thank you very much for your talk. Does anyone have any questions?
Yeah, I mean, you are considering the acylindrical action. I mean, the groove you have, the free-by-cyclic. So it acts on this calligraph jet. I mean, the Basarati jet by acylindrical. Is it your definition? What is the definition of? Yeah, here you are considering for acylindrical.
You're asking about the definition of the free-by-cyclic groups in general?
No, acylindrical. So you go.
Yeah, so this is not really relevant actually, this acylindrical hyperbolicity.
Yeah, that is fine, but I want to know.
Sorry, I'm not sure if you're saying
Because
anything,
my
but I
point
can't
is
hear.
there are so many hyperbolic automorphisms of this FN for which you have some flaring. I mean, the action of that group on the Basarati jet, that is not acylindrical. So this is why I'm asking here, what do you mean by acylindrically hyperbolic? I mean, the free-by-cyclic group, that is an H-N extension of FN, right?
Right. So I don't know what's the space that you're acting on to get acylindrical hyperbolicity.
This is the Basarati, I mean, the Riff's definition.
Right. Sorry, I'm afraid I don't really understand your question.
So what does it mean by acylindrically hyperbolic group here? I mean, you are saying
okay, what is it?
Yeah.
Right. It just means it admits an acylindrical action on a hyperbolic space.
I see. Okay. You are not looking at this as a fundamental group of some graph of group. This is an agent and extension, so that is why I'm.
I mean, as I said earlier, there are many different of these splittings, right? So for any single free-by-cyclic group, there isn't a canonical way to express as a free-by-cyclic group as this agent and extension.
Yeah, fine. I mean, I don't know about the equivalenceness of these two definitions. So one is due to these Riffs, and you are saying this group acts on some hyperbolic space by acylindrically.
Right.
I have an unrelated question, Monika. So, do you expect your result to be true without the extra refers hypothesis? Do you expect to have quasi-isometric rigidity?
That's the dream. That's the dream. But yeah, a whole different set of tools is required. Yeah. So you'd need to bypass Sam's result somehow. And I do expect it to be true, but I think there's still a bunch of tools need to be developed for that.
Okay.
Yeah.
And you have one theorem that virtually isomorphic. So for that, my point is there any geometric motivation to consider this group G? I mean, any examples or?
Well, so
this one.
So examples of the groups that satisfy these It's the refers and finite cohomological I mentioned, though, that we know of many are subgroups of rags. But yeah, the reason why I have to use refers is for this result, to apply this result of Sam Fisher, because and in fact this result is not true if you drop the refers condition. So just knowing that a bunch of your L2 Betty numbers vanish doesn't necessarily tell you that your group maps onto Z with nice kernel. So yeah, okay. So this is why this refers condition is necessary for this theorem and then for my theorem. But yeah, as I said to Macarena, if to get rid of the refers condition, I really need to bypass this theorem and think of a different way of ensuring that my group, that this mysterious group that's quasi-isometric to a free-by-cyclic group, it admits some map onto Z.
Okay, well that's
because you. Yeah,
that's
sorry. Yeah, we're running over. Yeah.
I will press